Hi guys, so just continuing on from the last video, we're going to have a look at the ionic product of water, also known as Kw. We're going to look at water dissociating, what Kw is, what the equation for Kw is, how Kw varies with temperature, and how we can work out the pH of water and the pH of a strong base using Kw. So let's get straight into it. First of all, in all aqueous solutions and pure water, the following equilibrium occurs. So water partially dissociates into hydroions and hydroxide ions. Now, we know there's an equilibrium present because there's this reversible symbol. That tells us there is an equilibrium. Now, one thing to note that's really important, which is another really common exam question, is that fact that water concentration is very large during this equilibrium. It's much more bigger than the concentration of the other ions, so normally we can assume it's constant. Even if there is a change, it's pretty much negligible. It's constant. Also, the equilibrium is positioned very, very far to the left. When we say far to the left, it's positioned right here, favoring the concentration of water, again contributing to the fact that it's super large. Now, since there is that equilibrium there, what we can do is form a Kc expression. Now, Kc is the concentration of your products over your concentration of reactants. You should remember that from year 12 chemistry during the equilibrium topic. Now, if we do that for this expression and a specific example for water, we will get the concentration of hydroions times the concentration of the hydroxide ions all over the concentration of water. And that's our expression for Kc. We're going to need this because the ionic product of water, Kw, is given by this equation. Kw equals Kc times our concentration of water. Now, getting our expression and inputting a little expression for Kc into this function will give us this following expression. Kw equals the concentration of hydroions times the concentration of hydroxide ions all over the concentration of water, again times the concentration of water. However, we can now cancel these waters out. And that will give us this final expression that Kw is equal to our concentration of hydroions times our concentration of hydroxide ions. If you're very good with units, you might be able to recognize it straight away. But if you put mole dm cubed into both of the concentration boxes, you will get the units of Kw being mole to the power of 2 dm minus 6. Now, Kw at 25 degrees Celsius or 298 Kelvin is 1 times 10 to the negative 14. A good way to remember this, it's very similar to the pH scale because the pH scale is 1 to 14. That's a good way of remembering it if you need it. But it's really important that you do remember that value. Now, let's now have a look at why, when temperature increases, why Kw also increases as well. So in all aqueous solutions and pure water, we did have that following equilibrium happen. And you'll notice that this actual equilibrium has the enthalpy of an endothermic reaction. It's positive. So if you notice the trend, as temperature increases, Kw also increases. The reason to why that is, if you remember from the equilibrium topic, if you increase the temperature of an endothermic reaction, that favors the right hand side. Now, what is on the right hand side? On the right hand side, you have the hydroion concentration and the hydroxide ion concentration. You're favoring that side and you're increasing their concentrations. The reason to why is it wants to counteract that equilibrium, wants to counteract that change, the change being the increase of temperature. Since we increase these guys and we refer to Kw's equation, it being the concentration of hydroions times the concentration of hydroxide ions, you've now increased these values right here, and when you multiply them together, these increased values, you're now going to get a bigger value for Kw. And that's why Kw increases with temperature. Another very, very common exam style question. Let's have a go at some of these questions. Now, find the pH of water at 25 degrees Celsius. So, let's first write down the equation. Kw equals the concentration of hydroions times my concentration of hydroxide ions. You should remember at 25 degrees Celsius, the value of Kw, it's 1 times 10 to the negative 14. Now, we're in this little tricky scenario because we don't know the concentration of hydroions, neither do we know the concentration of hydroxide ions. But what we can do is assume one thing. Water splits equally into a hydroion and hydroxide ion. For every one water splitting, there's one hydroion and one hydroxide ion. The concentration of these two, therefore, will always be equal. So, we can replace the hydroxide ion concentration with another hydrogen concentration symbol because they're the same. Now that brings the question, why didn't we replace the hydroion with the hydroxide ion concentration symbol? So why didn't we do this? Now, although this is technically right, it wouldn't be useful because we're trying to find pH. pH from last lesson is minus log 10 of the concentration of hydroions. And therefore it'd be more useful to find the concentration of hydroions over the concentration of hydroxide ions, which would provide no value in working out our pH. Hence why we replace the hydroxide ion concentration here with the hydroion concentration. So now, if we have two unknowns multiplying together, that will put hydroion concentration now to the power of 2 squared. So now we can square root both sides to get rid of that squared, and that will give me 1 times 10 to the negative 7. And that will be my hydrogen ion concentration. As we mentioned before, we can use this to find our pH. So minus log 10 or 1 times 10 to the minus 7. And that will give me a pH of 7. Now, one thing you want to make sure you don't do is just write 7. You have to put 0, 0, as we mentioned last lesson, because pH should always be to 2 decimal places. Perfect. Explain why the pH of water is neutral. The reason why the pH of water is neutral is because, what we mentioned, the hydroion concentration is always equal to the hydroxide ion concentration. Perfect. Question 3. Find the pH of 0.012 mole dm cubed of NaOH when Kw is 2.9 times 10 to the minus 14. So, this time we know our Kw, but straight away, first things first, let's write our Kw expression. Our Kw is 2.9 times 10 to the negative 14. Now we do know our concentration of hydroxide ions, but first let's look at our equation of dissociation. A lot of people forget about this step, but it's really, really important because sometimes your ratios can mess you up. So, sodium hydroxide dissociates into sodium and hydroxide ions. It's a strong base. That's really important because all of this will fully dissociate into sodium and hydroxide ions. So since I have 0.012 of this, it will completely dissociate to provide me 0.012 of hydroxide ion concentration. Therefore, my hydroxide ion concentration is 0.012 mole dm cubed as well. I can now input that into my equation. 0.012, and I can now divide both sides by 0.012 by doing the inverse. So doing that will, let's see what that gives me. That gives me 2.416 ... times 10 to the negative 12, and that's the concentration of hydrogen ions. And finally, what we can do now is put this straight into the pH equation, because we now know our hydrogen ion concentration, and that is pH equals minus log 10 of 2.416 ... I'm putting the exact value that I have on my calculator into the minus log 10 by using the saving function on my calculator. And that's going to give me 11.616. and to 2 decimal places, that's going to be 11.62 to 2 dp. Perfect. And that would be my final answer. Let's have a look at some real exam questions. Strontium is an element in group 2. Calculate the pH of 0.01 molybdenum cube solution of strontium hydroxide at 10 degrees Celsius. You may assume that the strontium hydroxide is completely dissociated in this solution. At 10 degrees Celsius, the ionic product of water, Kw, equals 2.93 times 10 to the minus 15 mole to the power 2 Gm minus 6. Okay, so first of all, as we should always mention, and always do, is strontium hydroxide looks like this. And it's completely dissociated, which means it's a strong base. Let's have a look at what it would dissociate into. Strontium ions and 2 hydroxide ions. As you can see, we now have a really harsh ratio. If you didn't do this step, you'd mess up and you would lose a couple of marks. So 0.01 mole dm cubed of strontium hydroxide ions, that's got a ratio 1 to 2. So to get to this concentration of hydroxide ions, it's times by 2, 0.02. Therefore, the concentration of my hydroxide ions is 0.02. Perfect. Now, let's write our Kw expression. And do we know our value for Kw in this case? Yes, we do. It's right here. Kw is 2.93 times 10 to the negative 15. And we don't know our hydrogen ion concentration, but we can definitely work it out because we now know our concentration of hydroxide ions. Now, doing the inverse and dividing both sides by 0.02, I can do 2.93 times 10 to the negative 15 divided by 0.02. Make sure to use brackets in your calculator, by the way. So what I've done is did this and then divided by 0.02 because I've got a lot of things going on, a lot of functions going on. So using brackets is super important. And I get 1.465 times 10 to the negative 13 as my hydrogen ion concentration. Now I can put this into a pH function, minus log 10 of concentration of hydrogen ions. 1.465 times 10 to the negative 13. And my pH comes out to be, let's have a look, 12.834 dot dot dot, 2 decimal places, that's 12.83. Perfect. Nice, let's move on to the next part. And as you can see from the mark scheme, that's perfectly right. So this question is about pH, and pure water dissociates slightly, as we already discussed. You can see that they're given the same expression, that water dissociates with that equilibrium, and that the equilibrium constant for Kc is the concentration of hydrogen ions times the concentration of hydroxide ions all over the concentration of water. Now, the ionic product of water, they've shown you the simplified Kw expression. Now they said explain why water is not shown in the Kw expression. As we said before when we cancelled it out, the reason why is because water concentration is large, constant, and the equilibrium is positioned far to the left. Perfect. Let's move on. Table 5 shows how Kw varies with temperature. So as you can see, as the temperature is increasing, the Kw value is also increasing. Explain why the value of Kw increases as the temperature also increases. So, as we mentioned, it's always to do with the fact that it's endothermic, hence why they've given you a value which is positive for enthalpy. So I'm going to write the E expression, or the equilibrium is endothermic in the forward direction. So when temperature increases, the equilibrium shifts to the right to counteract the increase in temperature. Therefore increasing the concentration of H+ ions and hydroxide ions, and that therefore provides a higher kW value when multiplied. 6.3. Give the expression for pH. Calculate the pH of pure water at 50 degrees Celsius. Give your answer to 2 decimal places. Explain why water is neutral at 50 degrees Celsius. The expression for pH is equal to minus log 10 of my hydrogen ions concentration. The calculation of pH of pure water at 50 degrees. Looking at the previous question, they've actually given me the kW value right here. That's one thing that's quite tricky from AQA. They've used the last part of the question. It's 5.48 times 10 to the negative 14. So 5.48 times 10 to the negative 14. And again, just before, expression for kW is my hydrogen ion concentration times my hydroxide ion concentration. And again, we should always know that the water dissociates equally. In the concentration of hydrogen ions is always equal to the concentration of hydroxide ions. They should always be equal. That's a rule that you'll see throughout this entire topic. So we can actually replace the hydroxide ion concentration with the concentration of hydrogen ions because they're the same. And therefore, when they're multiplied, it's squared. When we have a squared, we want to get rid of that. We're going to do the inverse, which is square rooting both sides. So square root of 5.48 times 10 to the negative 14 gives me 2.3409 ... There's so many values in my calculator. Don't need to write them all down. And that gives me the concentration of hydrogen ions. I'm going to put that into my expression of pH, which I just gave the answer for right here. And that's minus log 10 of 2.3409 ... Again, I'm going to use the exact value by using the storage function on my calculator. I'm not going to simplify it. And that gives me pH value. So minus log 10 of my answer was 6.6306 ... pH is 6.63. So we got a value, oh again that's 2 decimal places. We've got a value of 6.63, but why is water actually neutral at 50 degrees? Because my value is actually saying differently. It's saying otherwise. So the reason to why that actually is always neutral is because the concentration of hydrogen ions should always be equal to my concentration of my hydroxide ions. Let's have a look at the mark scheme. So 6.1, concentration of water was almost constant, or it's very large, or its equilibrium lies very much to the left, or you could have said the other points as well. Equilibrium is endothermic in the forward direction. Equilibrium shifts to the right hand side to oppose the increase in temperature, and that's what we needed to say. 6.3, we had the pH expression. We did the squaring root of 5.48 times 10 to the negative 14. We put our value into the pH function and got a pH of 6.63. Perfect. And we got marking point 4 by saying the concentration of hydrogen ions is always equal to our concentration of hydroxide ions.